Kona. Welcome to my talk on Gaussian primes called Stuck in a Gaussian Moat, an overview of an open problem. In this problem, I'm going to be talking about the open problem that is Gaussian moats. And in order to do so, I'm going to first cover what Gaussian primes are, and then I'm going to cover the symmetry of Gaussian primes. After that, I'm going to introduce you to the problem, and then talk about some similar problems, one in the real numbers, and then a more complex problem of lines in the complex plane. After that, I will get into recent research into this open problem and the strides that some researchers have made, including Jordan and Rabung's construction, and then Gethner, Wagons, and Wick's progress into the question, and lastly, Das's proposed algorithm into finding new Gaussian primes. So to start off, I'm going to define Gaussian integers. We notate the ring of Gaussian integers as Ci, where the Gaussian integers are the complex numbers z is equal to a plus bi, where a and b are integers and I is equal to the square root of -1. Now, the great thing about complex numbers is that they form a plane. So if you let the real part of z be the x-axis and the imaginary part of z be the y-axis, then for every z in the complex field, there is one point on the Cartesian plane, and for each point on the Cartesian plane, there is one z in the complex field. So if you had the complex number z is equal to 3 plus 2i, that corresponds to the point on the plane 3, 2. Now, a Gaussian prime is a Gaussian integer z is equal to a plus bi that satisfies one of the following properties. If neither a nor b is equal to 0, then a plus bi is a Gaussian prime if and only if a squared plus b squared is equal to p, where p is an ordinary prime, or p is a prime in the real numbers. So in the Cartesian plane, this would be any z's that are not on an axis. Now, the second requirement for Gaussian primes is that if it's of the form c or ci, so one of the ones that is on an axis, it's prime if and only if c is an ordinary prime that is congruent to 3 mod 4. So if we're looking at some examples of these primes, let's first look at different ones that would satisfy or not satisfy the first requirement. For example, u is equal to 1 plus 2i does satisfy it because 1 squared plus 2 squared is 5, and that is an ordinary prime. However, v does not satisfy either of these requirements, though both of its real and imaginary components are ordinary primes. V is not a prime, a Gaussian prime. Similarly, w is a ordinary prime, but it is not a Gaussian prime as it is not 3 mod 4, and so it does not meet either of our requirements. However, x does, and we can see that y and z are just the same, with y not meeting the criteria, but z meeting the criteria. Now, you might already be noticing some of these patterns, but if you look at our graph of Gaussian primes with norms of less than 100, you can see a clear symmetry, and that's not just a coincidence. The way that the definitions for Gaussian primes is set up is innately symmetrical. So if you look at our axes, whether or not you're looking at the real axis or the imaginary axis, whether or not an integer is going to be prime is the same. So there's the same requirements for both axes. And that's also stays the same whether it's positive or negative. Now, if you're looking at the first requirement of our definition, so these Gaussian integers that are not on the axes, if you switch A and B, the sum is going to remain the same. So there is that reflection over x is equal to y, or a reflection over the line that goes through the origin with slope 1. And that's because a squared plus b squared is going to be equal to b squared plus a squared. And because of the squares, if you make either one of them negative, there is going to be, you're going to get the same answer as to whether or not it is prime. And so this means that the Gaussian primes have an 8-fold symmetry, which is incredibly helpful when we're looking at our Moat problem, because it means that we don't have to consider the whole complex plane. We only need to consider just an eighth of it when we're doing our calculations. So this problem of the Gaussian moats is it possible to walk to infinity with bounded steps of length k, stepping only on Gaussian primes, starting, of course, at the origin? Another way to phrase it is, do these Gaussian primes become arbitrarily far apart the closer one gets to infinity? So to rephrase that into a smaller and more manageable scope, a similar problem is moats in the real numbers, and whether or not one can walk to infinity on the real number line, taking bounded steps of length k, using only ordinary primes as stepping stones. Rephrasing this, we can look at whether or not you can have k composite numbers in a row. So if you can prove that there's always going to be k composite numbers in a row, you can prove that you're not going to be able to take that step, because there's going to exist those numbers that you can't step over. And we can construct those numbers as shown on this slide with k plus 1 factorial plus 2, and then the next one being k plus 1 factorial plus 3, all the way up to k plus 1 factorial plus k plus 1. So looking at the first one, we know that 2 divides both k plus 1 factorial and 2, and then the next one, 3 divides both k plus 1 factorial and 3, and this continues all the way up until k plus 1 divides k plus 1 factorial and k plus 1, which means each one of these integers has a divisor, meaning each one of these is composite. And because we have from 2 all the way up to k plus 1, there are k of them, which means there will always be k composite integers next to each other on the real number line. Before we get into, before we add in a whole nother dimension, let's continue to look at lines, and let's consider the question, is there a line in the complex plane where one can walk to infinity on these bounded steps of length k, using only Gaussian primes as stepping stones? So is there a line in this plane where one might be able to walk to infinity? The first piece of information that Gethner et al. Uses is a lemma. Let L be a line that contains at least 2 distinct Gaussian integers. Then there exists a Gaussian integer m not equal to 0 and a Gaussian integer b such that the real and imaginary parts of m are relatively prime, and the Gaussian integer z is on the line if and only if there is an x in z such that z is equal to mx plus b. The other piece of information that Gethner et al. Uses is a theorem, the Chinese remainder theorem, which is supposing that a sub I and m sub I are contained by zi, and you're supposing they are such that the m sub I are relatively prime in pairs. Then we know that there is a solution to the system of linear congruences. X is congruent to a sub 1 mod m1, x is congruent to a sub 2 mod m2, so on and so forth, up until x is congruent to a sub s mod m sub s. And if A is the smallest such solution, then all solutions are given by x plus mn, where n is contained by zi, and where m is the product of the moduli. Restated, the solution is the unique modulo m. Using these two pieces of information, Gethner et al. Is able to prove the theorem, the following theorem. Let L be a line that contains at least two distinct Gaussian integers, and let K be a positive real integer. There is a Gaussian integer W on this line such that all Gaussian integers within the distance K of W are composite. In other words, you cannot walk on a line in the complex plane to infinity, taking bounded steps of length K and only stepping on Gaussian primes. This takes us to the recent research in this open question. Now, Jordan and Rabung were able to find a moat of width root 10, which you can see here in the graph below. Of course, this is only an eighth of the plane, but as we know, the symmetry of the Gaussian primes allows for the investigation to be into only that eighth of the plane. Now, Jordan and Rabung created a construction, which means they went through and they found each of the composite numbers in this moat, and they found each of the vertices to prove that nothing was within root 10 of any of these primes. Now, of course, this research can be quite tedious and time-consuming, especially if you're doing all of these sorts of calculations by hand. Luckily for us, modern computers are able to do this very quickly. Gethner et al. Was able to use Mathematica to find a lot more information on Gaussian moats. As you can see from this table, they found a moat of width root 26, and they're able to gather a lot of information on each of these moats. Now, no new theorems or conjectures have been made from this table. However, the information that Gethner et al. Has gathered has provided us a lot more context into Gaussian moats and is being used by other researchers, including Das, who has proposed an algorithm to find primes within a selected area. Das' algorithm only looks in the first eighth of the complex plane, using that eighth-fold symmetry that we mentioned earlier. Das' algorithm supports the idea that one would not be able to walk to infinity using steps of bounded length. Das theorizes that primes will become increasingly sparse as one approaches infinity, and therefore the Gaussian moats would only grow and become arbitrarily large. With all of the advancements that are being made in computers today, it's only a matter of time before someone develops an algorithm to find larger and larger Gaussian moats, and I can't wait for that day. Thank you.